Now let's take partial derivatives a little further here. Now we're dealing with a function fxyz. In the previous video, it was only dealing with fxy, so that was a three-dimensional function. This here is a four-dimensional function, and my independent variables are x, y, and z. So now as we go through this, the x plus h, I'm still going to plug in for x, for f of x, or fx, I should say. And for y, I'm going to plug in y plus k, and that's going to be for my fy. And then for z, it doesn't change, it just adds that extra component here. So it's going to be z plus m, and for z, for fz. So that's the only difference here. So it's nothing new, it's just that limit definition for different functions and different letters. That's all that is. So anyways, the next thing I want to talk about here is this equality of mixed partial derivatives, Clairaut's theorem. And I know I said that wrong, but I did the best I could. All right, now this says, suppose that fxy is defined on an open disk D that contains the point AB. If the function fxy and fyx are continuous on D, then fyx equals fxy. And what's nice about that is if I can tell that these are continuous, then I can say that they're equal. And this theorem actually comes in handy later on. We're actually going to use this theorem to prove a point so that we can use some more tools. And that's what this is going to help us with later on. But just kind of keep that in mind, though. If these partials, these second partials here, are continuous on D, then the partials are equal. Very nice. So let's try these problems here. So this says d2 of f dx dy on the bottom there. And to the right here, I put all of the different forms for that here. So if we're looking at this df squared, that's a second derivative. But I'm first going to take df dy. So when I see this is what I see. Or I could put my f in there. Don't forget my f. So this is what I see when I see this. And that's what you see down here. Let's see, where's that at? That's this one here. So you kind of work from the right to the left. That's kind of what we're doing here. Actually, that is what we're doing here. So that's the notation. Or I could say this as well, that this here is equal to fyx. So this means I'm going to take the derivative of y first. This notation here tells me I'm taking the derivative of y first. But what's weird about it is they're switched around, at least the notations. And that's what we see there. So be careful. When I see the yx in this form, I take the fy first, and then I take the derivative of that with respect to x, what I end up with from the fy. And for this one, it's the same. So this one, I look at a function notation, and over here, it's just straight across. So that's something I wanted to point out to you first. So now we're going to do this the simple way, no limit definition here. All right, so that means that we have to do df dy first. So that's my variable, and everything else is constants. So that's to the first power. So my answer for this is going to be x cubed, z squared. But let me put it in the right notation. I got to make sure it's equal. So I have to write x cubed z squared. So now, if I'm going to do the derivative with respect to x now, that means this is my variable, that's a constant, the z squared is. So I'm going to bring that 3 down. So now that's going to be 3x squared. So this is going to be 3x squared z squared, and that's my final answer. Now for the one down below here, this is a different notation. that we're using here. And that's the other notation that I said what was equal to this here. So this is going to be fz. So I'm going to take this function here with respect to z. So with respect to z, that's going to be 2x cubed y z to the first. And again, this is my constant because it's with respect to z. So that's my answer for this so far. Now, maybe I shouldn't have written it this way. Actually, I should have done this. Let me go back on this one. I'm just going to take this piece right here. And what I should have said was f of z equals this here. That's what I should have said. And then I can say f of z of 1, 1, 1 is actually equal to 2, 1 cubed times 1 times 1. That's really what I should have written here. And this is going to equal 2. Because this is saying I want f of z when I plug in 1, 1, 1 as my point. So this is our answer for this one. So yeah, I should have written this first. So that's our answers for these.